In this presentation, I'm going to talk about the different parts of a problem formulation from the context of multi-objective optimization. The central element of a problem formulation is a model of a system. I'm not going to discuss your model in detail. We assume you already have something you want to optimize. Instead, I'm going to define what's important about your model from an optimization standpoint. What's important for optimization is the decision variables and the system responses. Decision variables come in, we run the model, and responses come out. Usually multi-objective optimization doesn't operate directly on system responses. Instead, we define constraints, goals, and objectives. These are terms that come to us from multi-criterion mathematical programming, although we are using them for multi-objective optimization instead. In the rest of this presentation, I'm going to illustrate what the constraints, goals, and objectives are. First, I'm going to orient you to some visuals that I'm going to use for the rest of the presentation. The top two graphs show the domain over which the decision variables can vary, which we call decision space. I've marked contours for two response functions in the decision space. When we do multi-objective optimization, we vary the decision variables to try to get the responses we want. The bottom graph shows the space of the response functions. It's empty right now, but we're going to slice it up on the following slides. Here I'm illustrating decision variable constraints. Decision variable constraints identify a region in decision space that contains acceptable solutions. When a solution satisfies all of the constraints, we call it a feasible solution, and the region where these solutions are found is the feasible region. We can see the effect on the system responses in the bottom plot. We can also put constraints on the responses. Here I show the effect on the decision space of putting a constraint on each response. Where the two dotted contours intersect is the only feasible region in decision space. So choose your constraints carefully, otherwise you won't have any feasible solutions. Goals are like constraints. They put limits on the responses. But instead of saying what responses are unacceptable, goals indicate what response level would be satisfactory. If a solution exceeds that goal level, that's great, but we're not going to push to improve a solution further if a goal has been met. Finally, I'm going to talk about objectives, since that's why we're all here. Objectives are generally functions of your system responses that you want to minimize or maximize. You might also use the system response directly if it lines up with your preferences. In any case, by specifying an objective, you're saying, I want this number to be as big or small as possible. Usually two or more objectives will conflict with each other, and this gives rise to what's called a Pareto frontier. These are the solutions that can't be improved in one direction without giving something up in another objective. And what multi-objective evolutionary algorithms try to do is find solutions that approximate this Pareto frontier. I'm going to leave you with the definitions I've presented here. This concludes the presentation.